Hi everybody, welcome to the Circuits 1 review. My name is Arya Bloom.
My name is Justin Bond.
In this video, we're going to go through, one of each of the big types of questions that you might see on your final exam and kind of go start to finish the key concepts to prepare you for, doing well in this class. So we're going to start off with question number 1, a nodal analysis question. So this question wants you to find the voltages at nodes A and B using nodal analysis. So first things first, we're going to have to set up our KCL equations. So we're going to have we'll start with the voltage at node A. We're going to have all of the currents coming out of this node to sum and equal to 0. So let me just draw that. And what you get out of this KCL equation should look something like this. And then we're going to do something similar with B. So current coming out, and then as you can see, this independent current source over here is going into B. So instead of adding it in our KCL equation, we're going to subtract it because it's going into the node instead of out of the node, which will give us an equation that looks a little something like this. We have all of our values for R1, or for our resistors, for our voltage source, and for our current source over here. So if we plug this into our calculator, I'll give you guys a second to figure that out, or you could pause here if you'd like. That'll give us voltage at node A is equal to 5.827 volts, and the voltage at node B is 2.378 volts. So what we're going to do next is we're going to solve the same circuit using mesh analysis, and we're just going to compare our answers. Since it's the same circuit, we should get the same values for VA and VB. So to start off, I'm just going to label these closed loop currents as IX, IY, and IZ. And we're going to have to set up our KVL equations. So we'll start off with loop X. We'll get an equation that looks something like this. So since we're going into the negative terminal of this voltage source, we get a negative voltage source. And then for the rest of it, I'm just going to assume positive convention. So plus IX R1, and then IX minus IY. As you guys could see, they're just going to kind of oppose each other in that direction across this R2 resistor. And then the sum of those voltages is going to equal to 0. And then next we'll set up our IY KVL equation, which gives us this. So we'll start off with resistor number 2. Once again, we're going to assume positive convention for all of these resistors, or all of these currents. So IY minus RX times this R2 resistor is how we get that. IY going through R3, and then we'll have IY minus IZ times resistor 4. That should sum to 0. And then the last thing that we want to note, don't get freaked out about this. We see that IZ is just the opposite direction of this current source over here. So we could write that exactly down. IZ is equal to negative 11 milliamps because it's given that IS is 11 milliamps. So when we plug this into our calculator, these three equations into our calculator, we should get current values for IY and IX. X, IY. So over here, we'll move over here to find the voltages. So the voltage at this node is going to equal to Vs minus Va. That voltage drop across that resistor is I sub X times R1. So rearranging down here and solving for V sub A, we get 5.827 volts, which is consistent with what we got in part A of this question. And then we want to move on to VB. VB, we could do the same thing. We want to calculate the voltage drop across this resistor to get the voltage at node B. So VA minus VB is equal to this current IY through VB, or through R3. So that gives us this equation. Rearranging and solving for VB, we get 5.287 volts minus IY, our current through that R3 resistor, multiplied by the value for our R3 resistor, and that gives us 2.377 volts, which, as we can see, is consistent with the answer we get up here. If you get a small, thousandth decimal place different answer, it's fine. It's probably just rounded differently with whatever numbers you used in part B. So for all intents and purposes, we can go ahead and assume that, we did our work correctly. Moving on to question number 2. Here's a Thevenin equivalent circuit question. I wanted to give you guys one with a dependent source because I know that they can be tricky sometimes. Don't be scared. It's not as scary as it seems if you know what you're doing. So step 1, we're going to solve for VThevenin as part A asks, and that begins with, once again, KCL equations. I prefer to do nodal analysis. This type of question looks like a nodal analysis will be the easiest approach to, get the values that we're looking for, so we'll go ahead and do that. So if we do nodal analysis at V1, or KCL at V1, we get, looks like this didn't, V1 minus, there you go. So V1 minus 12 volts over your 10 ohms, and then you have V1 minus your VO over 6 ohms, and then going in, you have 1.5 IX is equal to 0. And then equation number 2, KCL at VO. So we're going to do the same thing, VO minus V1 over 6 ohms. VO minus 0 volts over 8 ohms is going to equal to 0. And then equation number 3, we have this IX value. I'll put that in red for readability, this IX value. If you guys know, IX right here can just be described as, this voltage, or this voltage drop across this resistor. So V1 minus VO over your 6 ohms. So that'll be our third equation that we plug into our calculator. Once again, use the linear solve method or function on your calculator to obtain values for V1, VO, and IX. And you'll get this over here. This gives us 10.66 volts for VO, and as you guys see, the voltage from VO across this 8 ohm resistor to ground is the same voltage as from A to B. So VO is going to be the same as VThevenin, which is this 10.667 volt value that we have over here. Next, it asks us to solve for RThevenin. Now this is where it can get tricky, but don't be alarmed. The first thing you want to do is turn off your independent sources and add a test source. So to turn off a independent voltage source, you turn the source to 0 volts, right? So 0 volts. And if you think about what that means within the context of the circuit, since there's a 0 volt drop across this, it essentially turns into a wire. So I'll just do that right there so we can actually see what we're doing. So that turns into a wire, and then you're going to want to put on an independent test source. I'm going to choose to use a current source to make nodal analysis just a little bit easier. And I'm not going to assign a value to this. You'll see why. I'll just call it IT for iTest. So we'll once again begin with nodal analysis. Oh, wow. That is KCL at V1. So you get V1 across this 10 ohm resistor to ground now, as you can see, because this voltage source is shorted. And then you add V1 minus VO over this 6 ohm resistor. And going into this again, you have IX. We'll subtract IX, and instead of calling it IX, since we know what it is now, we'll just call it 1.5 times V1 minus VO over 6, which is equal to 0, because V1 minus VO over 6 is equal to IX. So we can just substitute that in. Equation number 2, we'll do our KCL at V0. Excuse me, I kind of thought that all these numbers would still be here, but it's fine. We'll work on through it. So we'll have VO minus V1 over our 6 ohms. Then we'll have VO over 8 ohms down to ground. And then going into the node, we see we have this iTest source. So we'll subtract that, and we'll set all of that equal to 0. So this is what trips a lot of people up, is you have 3 unknowns, but only 2 KCL equations. But one thing that is important to remember is that we're solving for R Thevenin, which is equal to V Thevenin over our iTest value down here. So we have VO, if we remember from the last part, VO is what we can call V Thevenin. So we have 2 of the elements that we need. We just have to find a way to get these 2 equations in the form of VTH over IT. So what I'm going to start off by doing is I'm going to take this equation 1, and I'm going to solve for V1 in terms of VO. So, okay. Just expanding that fraction over there, you get this, and then I'll move around, keep the V1 terms on the left side, the VO terms on the right side. We get V1 over 60 is equal to negative VO over 12, which gives us V1 is equal to negative 5 VO. So now we could plug in negative 5 VO for V1 in our KCL equation number 2. So that gives us this over here. You just plug that in right there like that. And then we have, simplifying, we get 9 over 8 VO is equal to I Thevenin. And then rearranging for VO, which remember is equal to V Thevenin, we get VO over IT is equal to 8 over 9, which is equal to our R Thevenin value, so 0.889 ohms. So there you have it. There's your Thevenin voltage equivalent that we obtained up here, 10.667 volts. And we have our R Thevenin voltage of 0.889 ohms. And part C asks us to redraw the Thevenin equivalent circuit. So we need our Thevenin source, our Thevenin resistance, and then our 2 terminals A and B, our Thev, and we've determined that this is equal to 10.667 volts, and that this is 0.889 ohms. And then there you have it. There's your Thevenin equivalent circuit. Moving on to question number 3, a an RC step response or natural response question. It wants us to find the current through the resistor, the current through the capacitor, and the voltage across the capacitor for t is less than 0 and t is greater than 0. So first off, what we want to do is we want to redraw the circuit for t is less than 0 before this switch opens, and that circuit is going to look like this. So as you guys know, when a capacitor is fully charged, it acts as an open circuit. So that essentially allows us to ignore these two components here while we're doing our analysis for t is less than 0. So to find the voltage across the capacitor is essentially the same as the voltage across this 2 kilo ohm resistor. So we can just do voltage division to find that our initial voltage across our capacitor is 8 volts. Since we have an open over here, we know that the current through the resistor is going to be 0. So that makes our lives easier, no math there. And then to find the current through our resistor, simple Ohm's law, V over R is equal to I. So you have your 4 kilo ohm resistor in series with the 2 kilo ohm resistor. So our total resistance is 6 kilo ohms. So 24 volts over 6K gives us an initial voltage through the resistor of 4 milliamps. The next thing we want to do is draw the circuit after the switch has been flipped. So that disconnects this part from the circuit, leaving us just with this. So we have an initial voltage across this capacitor, and just if you think about what's happening, it's just going to discharge current through this loop indefinitely, or not indefinitely, it's just going to discharge everything through this loop until the resistors absorb all of the power. So the form of the equation that I personally like to use for these kinds of questions looks like this. This works for your step and your natural response questions for RL and for RC. So you have whatever component you're solving for with respect to time is equal to the final value plus your initial minus final value times e to the minus t over tau. So first thing that we want to do is figure out what our time constant is. As I said before, this current is just going to kind of go through in this loop. So, these two resistors are in series. So we have our Req is equal to these two added together multiplied by our capacitance, which gives us a tau of 1 over 100. The next thing we want to figure out is the equation for the voltage across our capacitor. And another note, it really helps to label what components you're working with so you don't get confused as to, which currents you're using, which voltages you're using. If you make sure to write that V sub C and the entire time think about okay, I'm working across this capacitor. I know it sounds simple, but it helps a lot because a lot of moving parts can go into these kinds of questions. And the more you write down, the more you're helping yourself. So we knew from the steady state before the switch flipped that our initial voltage across the capacitor was 8 volts. And as I already said before, it's just going to kind of go through the loop indefinitely until there's no more charge and it's all been absorbed by the resistors. So our final voltage is going to be 0 volts. So if we plug that into this form of the equation, we get our equation for our voltage across the capacitor is equal to 8 times e to the minus 100t volts. Nice. So then, since we have our voltage across our capacitor, it makes sense to find the voltage or the current through the capacitor with respect to time. And we have this equation here. I is equal to c dv dt. So if we plug in our equation for V sub c of t and take the derivative of it with respect to x, we get negative 0.0016 e to the minus 100 t amps, which we can rewrite as negative 1.6 e to the minus 100 milliamps. So that gives us, our equation for I sub c of t after the switch is opened. And then to find the current through our resistor, we remember the current through a closed loop is going to sum to 0. So IC plus IR is going to equal to 0 because those are our two currents that we're solving for. So solving for IR, you get IR is equal to negative IC of t, which just gives 1.6 e to the minus 100 t milliamps. So that's how you do that.
All right, so moving on to number 4. This is an operational amplifier, and what they do is they can increase a voltage from the beginning to the end of a signal. And there are also some characteristics of an operational amplifier that you need to know for this class. We're going to assume every op amp in circuits 1 is ideal. Later on, that's not true, but for this class, you always have an infinite open loop gain, which essentially means that the maximum gain of the op amp isn't limited by any internal factor. It's always going to be based on the resistive network around it. You also have an infinite input impedance at the minus and plus terminals, so no current will flow that way. You also have the same voltage across V plus and V minus. So if you had a voltage at the bottom node here going to ground at the plus node, you could just assume that voltage is the same. And you also have 0 output impedance. So to solve this problem, we're going to use KCL. And we'll start with VA minus 0.5 volts over 10K plus VA minus V out over 25K equals 0. Anyway, so now we have this relationship to determine the voltages. The next thing you have to realize is that the voltage at node A is equal to 0. And that's because you have no current flowing into the op amp because of the ideal op amp assumption. And so we can just substitute that in for negative 0.5 over 10K plus negative VO over 25K equals 0. After this, we can just use algebra to solve for V out. So we have negative 0.5 times 25K over 10K equals V out, and that equals 2.5 times negative 0.5. So that would be negative 1.25 volts. So that's how you solve an op amp question with just circuits.
Configuration.
Yeah, an inverting op amp. There's also a non-inverting op amp where your V out and your V in would have the same sign. As you can see, V out is negative, V in is positive. There's also just a general formula for this. VO is always going to equal negative RF over RI for an inverting amplifier. And RF is the 25K in this case, RI is the 10K. And for a non-inverting amplifier, you have a different formula. That's all going to be given to you on your exam, I believe. And yeah, that's how you solve an op amp question. All right, so moving on to number 5, we've got the step response of a parallel RLC circuit. You may see a series RLC circuit. There's a totally different set of equations for that, but you should be provided all the necessary equations on your formula sheet. So the first thing you want to do to solve this type of problem is determine your initial conditions. So as we can see, it says the initial energy stored in the circuit is 0. That means the current across the inductor as well as the voltage across the inductor are both going to be equal to 0. Since we know the voltage is equal to 0, we can substitute V equals L di dt. That will tell us that di dt of 0 plus is also equal to 0. That's going to be useful later when we solve. So the next thing you want to do is determine if your system is overdamped, underdamped, or critically damped. And that is done by the ratio between your resonant frequency and your damping coefficient. So in order to find omega 0, your resonant frequency, you will find omega O squared, which is equal to 1 over LC. I've calculated that out. It's 1.6 times 10 to the 9 radians per second squared. Radians squared per second squared. After that, you'll find alpha. Alpha equals 1 over 2 RC, which is equal to 32,000. Therefore, alpha squared is going to be equal to 1.024 times 10 to the 9. Because we know both of these values here, this is greater than this. Therefore, we have a underdamped system. So now that we know the system is underdamped, we have the general form of the solution given by IL of t equals I final plus alpha 1 a1 e to the negative alpha t cosine omega damped t plus a2 sine of omega damped t times e to the negative alpha t. And omega damp is your damping coefficient. That is found by the square root of omega sub 0 squared minus alpha squared, which is equal to 24,000 radians per second. And you also know your I final. I believe that is given to you. That's right. Your I final is going to be equal to the 24 milliamps they gave to you in the problem. And that is because this is an underdamped system. The graph of an underdamped system looks like this. Over time, you're going to reach 0 gradually. So after this, you're going to want to find your A1 and A2 coefficients. A1 is easy. You just evaluate the circuit at time t equals 0. And your sine term is going to go away completely because it's t equals 0. Sine 0 is 0. You're left with 0.024 plus A1 e to the 0. E to the 0 is 1. So A1 is equal to negative 0.24. After that, what you're going to do is take the derivative of this entire system. That's why we found di dt at 0 plus when we started the problem. And I know this looks like a monster derivative. I promise you it's not that bad because you have two sine terms here. Those are both going to be equal to 0 because we're evaluating at time equals 0. So now we can plug in time equals 0. di dt at 0 equals 0 minus 32,000 A1 plus 24,000 A2. Since we have e to the 0 many times, that's just equal to 1. All your sine terms are going to be 0, like I said before. We know A1, so we can plug in the value of that, solve for A2, equal to negative 0.032. After that, we can plug this back into the general form of the equation, as we have up here. And we can solve, we know our alpha, we know A1, A2. So we can get I sub L of t equals 0.024, which is your I final, minus 0.024 e to the negative 32,000 t cosine 24,000 t, minus 0.032 e to the negative 32,000 t sine 24,000 t amps. And there you have it. All right, so moving on to number 6. This is a sinusoidal steady state analysis. So now we're dealing with alternating current. Don't freak out because it's not difficult at all. I know you might think it's hard, but it's not. What you want to do is express all of your capacitors and inductors in terms of a complex impedance, which can be done with these formulas here. As you can see, the impedance of a capacitor is going to be 1 over j omega c. The impedance of your inductor is going to be j omega L, omega being the radians per second of your alternating current. So here in this question, we're given the frequency, 60 hertz. First thing you want to do is convert that to an angular frequency by multiplying by 2 pi. So your omega is going to be 120 pi. After this, you want to redraw the circuit entirely in terms of complex impedances. So I've done that here. This capacitance is expressed as negative J265 instead of, it doesn't look like 1 over J, but 1 over J is negative J. So just having it like this will make it easier. After this becomes a simple voltage division problem. This is like week 1 stuff. So you can find your equivalent impedance. It's going to be this right here in series in parallel with the capacitor. So you have that plus your line here. Eventually what you get is a equivalent impedance of 3.63 plus J 7.62 ohms, which can be expressed in polar coordinates as so. And your calculator is powerful enough to where if you plug in rectangular, polar, whatever, it's going to do the conversions for you automatically. So don't even worry about on your exam converting everything as you're doing it. Just make sure when you have your final answer, have it in the form they want it in. So the next thing they want us to do is find the voltage delivered to the load, VL of t in the time domain. So first thing we're going to do is continue working in the frequency domain. And the voltage across the load is just going to be a factor of your input voltage times Z load over Z equivalent. It's just voltage division. So here, as you can see, you get 132 at an angle of negative 3.1 degrees. Make sure you're in degrees for this. They typically ask you in degrees. If you're in radians, it will make all your calculations wrong. So be very careful with that. And from this right here, we can express this in the time domain. 132 is going to be your amplitude. Negative 3.1 degrees is going to be your phase. So that can be expressed in the time domain as 132 sine of 2 pi times 60t minus 3.1 degrees. Also, make sure that when you express it in the time domain, be mindful of the trig function they give you here. As you can see, your V in is a sine wave. If that were a cosine, then you would want to express your answer as a cosine because of the way that sine and cosine waves can be transformed into each other. After that, they want to find the current delivered to the load, I load of t. So I load in the frequency domain is going to be V load over the impedance of the load, which is just your voltage over your equivalent or the impedance of the load in the complex domain. After that, you get 20.1 at an angle of negative 64.5 amps. That can be expressed in the time domain in the same way. So there you have it. All right, so moving on to number 7. It's our last question. It's 3-phase power. So first thing you want to do with 3-phase power, as you can see, we have a Y-connected source and a delta-connected load. You want to change that. If you recall delta to Y conversions from week 2 or 3, you can convert this into a Y-connected load. And all of these impedances of the load are the same. That makes your calculation really easy. They might not be the same on an exam, in which you'd have to do the whole delta to Y conversion. But because they're all the same, the impedance of your Y-connected load is 1/3 of the delta-connected load, which in this case is just 1 plus J 0.5. So the next thing you want to do is analyze one phase at a time. So we're going to designate a neutral on the line. So you have V from A to neutral going across the line. The line has its own impedance. You may or may not see a line impedance on your exam. And the only thing it adds is a voltage division. And your load is 1 plus J 0.5. After this, you're going to find the current of your line, which is VAN over Z load plus Z line. Your voltage is given to you. It's a 120 at an angle of 0 for A. You're going to divide that by 1.1 plus J times 1 ohms to get 80.7 at an angle of negative 42.3 amps. So after that, you can find V capital A capital N, which is going to be from the load to the neutral. And this is just the voltage across your load. So it's IL times the impedance of your load. That gives you 90.25 at an angle of 15.71 ohms. After this, you can use this formula here to find the voltage from A to B, which is the difference in the voltage between the two lines, it's root 3 times VAN at an angle of 30. This angle of 30, by the way, comes from the delta to Y conversion. Because if you were to draw out the delta configuration over this, the angle right here, theta, is equal to 30 degrees. So these formulas are specific to delta and Y. They should give you on the exam like a bunch of formulas for all the different scenarios. I believe we had that. So the voltage from A to B here is going to be 156 at an angle of 14.3. You would simply multiply the real part by a factor of root 3, and you would add 30 degrees to your angle to get that. So after this, we can talk about the complex power of the load. Your complex power is going to be done by S. S is the variable for that. So your S of your whole three-phase system is going to be 3 times the complex power of A, which is 3 times VAN times IL. So here you have that as 21.85 at an angle of 26.6 kVA, which are the units for complex power. This can be expressed in rectangular form as so. And then this will be expressed in the power triangle. So the power triangle, essentially what it does is it relates your real power to your reactive power and your apparent power. S is going to be your apparent power right here. Over here you have your reactive power, and down here you have your real power. And after this, you can find the power factor. The power factor is simply the cosine of the angle between your apparent power and your real power. If you don't know your apparent power, let's say you were to find real power and complex power, you could find that through a Pythagorean theorem, or you could find the angle directly using inverse tangent. Anyway, you should know that. It's all trig. Anyway, your power factor here is going to be 0.89, and that is a lagging power factor. Essentially, lagging power, what that means is that the current wave is lagging behind the voltage wave in your power delivery. And yeah, that's about all we have for the review session. Thank you very much for watching. Good luck on your exam, and I hope you enjoyed your time.